Imagine falling into a black hole. Einstein's theory says that nothing strange should happen as you cross the event horizon. You drift right through, unaware of the invisible boundary you just crossed. But a team of physicists suggests instead that you'd be burnt up by a wall of energy. A firewall right at the horizon. So how did we get here? Well, it begins in the early 1970s, when Stephen Hawking applied quantum field theory to curve space-time, and found a shocking result. Black holes radiate. Hawking's calculation is subtle but concrete. You see, the vacuum is not perfectly empty. Fields everywhere fluctuate with tiny bursts of energy. In the language of quantum field theory, we call these short-lived virtual particle-antiparticle pairs. They're virtual because they usually cancel each other almost immediately. How does this relate to black holes though? An often crude explanation that gets Hawking's point across is to imagine yourself near a horizon. The spacetime geometry, i.e. gravity, can separate those partners. One falls in and the other escapes to infinity and becomes a real particle. That escaping one is Hawking radiation. Two features of this radiation are crucial. First, it looks like heat. Its spectrum is set by a temperature proportional to the surface gravity of the horizon. Second, because it is thermal, the outgoing radiation carries no detailed record of the matter that formed the black hole. That's a problem. The matter that fell wasn't random. It had structure, information, history. In quantum mechanics, it's called a pure state, meaning that all details are preserved. But if the black hole evaporates and leaves only featureless heat behind, you've gone from a pure state to a mixed state, where the details are smeared out and unrecoverable. That's something quantum theory simply doesn't allow, at least for this case. Hawking himself argued for information loss for years. The community felt the tension as a real disaster. Either accept the information loss and break quantum mechanics, or find a mechanism that preserves unitarity, that is, the preservation of information in the quantum world, and forces us to rethink how horizons work. So, if you like neat universes where principles never fight, this is the point where things get messy. So, the question physicists began asking was a little rude but necessary. Does nature burn our information, or does it hide it in plain sight? Many of those theorists look for ways to save quantum mechanics without destroying general relativity. So, in the 1980s and 1990s, Leonard Susskind and I don't know how to pronounce his name actually. Here's an audio file.
Gerard het Hoofd.
Anyways, those two and others proposed the black hole complementarity. The idea is to ask what each observer actually sees. For an outside observer, they see information get scrambled at the horizon and leak out slowly in Hawking radiation. If you jump in, everything looks normal at the horizon. No searing wall, no fireworks. And you fall toward the singularity as general relativity predicts. Both accounts are allowed because no single observer can see both pictures at once. No contradiction, no paradox, right? This relies on an idea that you should know: quantum entanglement. Two quantum systems are entangled when their properties are linked so strongly that knowing one tells you something immediately about the other. Entanglement is not free. It obeys a rule called monogamy. Let's say particle A is fully entangled with particle B. It cannot be fully entangled with particle C. That constraint will matter soon. Then 2012 happened. Almeri, Marov, Polshinsky, and Sully made the contradiction unavoidable. Their arguments are based on simple premises almost everyone accepted. Quantum evolution preserves information, that is, unitarity. Conventional quantum field theory works outside the horizon, and free fall across a large black hole would be smooth. AMPS examined an old black hole, past what's called a page time. By then, it has emitted roughly half its entropy. At this stage, unitarity means that the early radiation already carries key correlations. Now, focus on a single Hawking quantum emitted late, call it B. For the horizon to look like empty space, B must be entangled with the partner inside the hole, call it A. But if the early radiation already purifies the system, B must also be entangled with some sort of early radiation, Monogamy forbids B from being fully entangled with both A and the early radiation. Algebraic contradiction, one of the basic assumptions, must go. AMPS gave a resolution to give up the smooth horizon, break the entanglement between B and A, and have B entangled with the early radiation and preserve information. Breaking the B-A entanglement means that the vacuum at the horizon is no longer a usual quiet vacuum. Instead, the near-horizon region is full of high-energy excitations. For an unfortunate astronaut falling in, that looks like a wall of highly energetic quanta. A firewall. The equivalence principle, a comforting rule that freefall feels like no gravity, would be violated at the horizon because the firewall makes the field discontinuous. The community reaction was immediate and furious, because this would mean losing one of GR's deepest and most intuitive statements. I mean, would you rather keep a smooth horizon and break quantum mechanics, or preserve unitarity and accept a universe where freefall ends in fire? That is a brutal choice AMPS forced onto physicists. It helps to be precise about what a firewall means and what it does not. The term might suggest a literal sheet of flame visible from afar, but it's not that. The firewall is a quantum state near the horizon with insanely large local stress energy, or in other words, gravity is so strong that it would suddenly cut your leg off as soon as you touch the horizon, right next to normal gravity just outside the horizon. In quantum field language, the short-distance entanglement that defines the quantum is disrupted. Break those correlations, and the vacuum excitations become energetic quanta. For someone trying to cross, the local space-time curvature and tidal forces become enormous on Planck scales, and would be fatal. Think of it like a messy neighborhood where every house is secretly connected to its neighbor via tunnels. That's how quantum fields behave in a vacuum. That entanglement smooths out the apparent particle content for a freely falling observer. Destroy the entanglement, and you populate those modes with energy. So firewalls are energetic because they are the consequence of preventing the usual vacuum entanglement, not because there's like a literal bonfire at the horizon. Fires don't exist in space. If this sounds extreme, remember why it was proposed. It is the simplest way within the assumptions AMPS accepted, to reconcile the bookkeeping of entanglement and preserve unitarity. But it does so by accepting the equivalence principle's failure in one very specific location. Obviously, the scientific field responded in multiple directions. No single reply is universally accepted, but everyone brought serious technical work. The best example is the holographic principle. It's the idea that all of the information inside the region of space can actually be encoded on its boundary, like a hologram on a sheet of glass. In practice, this principle is made concrete through a specific type of universe, which gives us the exact duality between gravitational theory in curved space and a quantum field theory without gravity on its edge. The important takeaway is this: if black holes are holographic objects, then the information about what falls might be always available at the horizon, as if the horizon was scratched, even if we can't see how. In this view, Hawking's calculation was missing part of the paradox. Another idea is replica wormholes. It sounds technical, but the result is elegant. Now, Hawking originally thought that the radiation given out from the black hole was entirely random, no information retrievable. However, we can compute the entropy of Hawking radiation using methods of quantum gravity. Wormhole connections between copies of the same universe dominate the calculation. To clarify, the wormholes aren't literally there. It's just a math trick. The result of considering replicas of the same exact universe reproduces the so-called page curve, where radiation entropy first rises but then falls, signaling that information does come out in the end. So Hawking's original thought that the radiation was entirely random was incomplete. It's just extremely hard to detect, but it still is theoretically possible to. It doesn't mean that the firewall paradox is fully solved, but it's the sharpest hint yet that the information is not lost, and horizons may remain smooth. There are so much more ideas, but honestly it's getting too complicated to say without making a separate video on each idea. But what can I say now is that none of the solutions is complete. The holographic picture works best in a simplified universe, but ours, not so simple. The common thread is this: we're searching for a way to keep information safe and preserve Einstein's smooth horizon. Whether firewalls exist depend on whether one of these rescue attempts ultimately succeeds. For the pragmatic people watching, the conclusion may sound unsatisfying. There is no consensus. But that is the point. The firewall paradox is a tool that exposes where our theories disagree, but that is where new physics is likely to hide. If you prefer a less philosophical take, for an astronaut falling into a large astrophysical black hole, there is no observational reason right now to expect an incinerating firewall. The paradox lives at the level of theoretical consistency, but clarity matters because it informs of how we build quantum gravity. What happens at the edge of a black hole challenges not just our equations, but our understanding of reality itself. If you want more deep dives like this, the kind that force us to rethink both gravity and quantum mechanics, hit subscribe and stick around, because black holes don't give up their secrets easily. But together we can peel back the layers of what the universe holds.